再讨论。
come back next
后面我们
time.
前面他们讲的
So
太大，
today I
我们
will
讲的很简单，
take about
就要好多铸件，我告诉你怎么做。
5 minutes of introduction and update. So it will not be deep technical discussion because later you will be more technical discussion. And tomorrow here in the afternoon for more of the cost and benefits. And in the afternoon we have 2 more case studies for our partners.
那你按理说你设计的那个父母肯定要3代啊。
是啊，我的意思是办不到的传统的
No，
东西做起来没有3代。
实际不是这样，因为我跟你说，我跟你这么说，我这么跟你说吧，我给你开了咖啡，然后呢，首先导入的是用合金一个成本纯水平更高，对，你合金一定在前提条件下，导热是跟缺陷。你中间有个窟窿，导热就差了呀。所以说要做好学，但是不会特别大。
Technology applied in your current process. Whatever focus on the high pressure die cast and the gravity die.
合金品你要想高是吧？把硅还导热下来。
啊，那肯定明显了。
哎，你
但是材料学定了之后你就
那改不了了。
对啊。
无解，除非还有一个改型，就是加硅，把那个硅把那个硅变小，也会，但这也很有限，都是一点点，你要直接的范围就是减少硬化，对吧？立马就显现出来了。苦吸力，做个苦吸力，因为你们不是这个芯片死当了，这下面是
苦吸力一般你比较专业的这个测量的方法。
啊，我们不标，ESDM标准来，我们要按照标准来，要不然大家不在一个语言上面讨论这个。你要按标准来。 ESDM 的标准，还有这个苦吸力等级表，或者说你什么，它是看
7 years.
不，其实最好的是最近太贵了，你扫一个然后呢？
但这个实际上就是很难去量化出来，
能吗？给你告诉你，孔的体积除上一个孔的体积除一个整体。
真的很难把握，它的孔角有很多孔嘛，很难去算。
你不可能看清楚，只有一个苦吸力，我下午给你。那就给他们做。我说自己来的。
对，扫了之后好像它也没有说算出一个
对，有给你一个数，我也不是量化的，量化的数。那个比较贵，还有一种办法就是
算密度呢，你觉得这个可行吗？
可行吗？
密度的这个
倒水里啊？
对，
也可以，其实挺准，但是这个密度你不知道分布，它可以知道这个大了，就只能说实在了，但你不知道这个缺陷分布在哪里在哪里。差不多那个挺准。还有一种就是，其实标准不是用 CT 的，因为太贵了嘛，它是用 X-ray 扫，在每个平方 square 里面有几个多大的东西了，这么要求的。有标准，但是这个应该是要求最高等级，有1、2、3、4、5、6、7等级，最高等级基本上就是小。其实那已经很多了，0.54啊，达不到了。CT 是0.1，CT 能看到0.1以下，1点1左右，0.1的0.1以上的都能看见，0.1以下太看不见。然后呢 ，X-ray 是0.5，X-ray 是0.5，那比还要好的，0.5 500个 euro。这就不差了，与其加上点多整的可以。真是这样的，你要说的0.3，其实就是他们 ESDM 标准比较高的。你看起来还不到一个 ESDM 标准，0505。对标准基本上
他们算这个数量大小，
他们数个数，大的几个4个几个这个区域和这个核心区域不能有其他的，能看到这个区域不重要，它可以一个1毫米或者是国标也有，这是最直接的。我下午有一个，我在上面有个可以扫，我给你看一下。
everyone
ทำเป็นคลิกเครื่องให้อาจารย์
ได้ครับได้
some of you
จะ
are
คอมอาจารย์
right
อ๋อ
มันล็อก
and I hope to see some of you to come back next time also. So today I will take about 45 minutes of introduction and updates. So it will not be in deep technical discussion because later Yu Feng will give more technical discussion and Tommaso here in the afternoon
ครับ
for more of the cost and benefits also. And in the afternoon we have 2 more case studies from our partners.
Everyone come here, you want to be good path. You don't care what's you only care how to solve, how to get good path. That's why you come here. Now, let's talk about how to make a path. My presentation will talk about the concept and the principle of GISS technology apply in your current
Yes, almost.
product you change it.
I know, but I can actually. Oh, the later. Okay.
คลิกเกอร์เนาะ
ครับ
Okay, we will start the afternoon sessions and we have some changes that I will do product review first, maybe 5 or 10 minutes. And then Yufeng will lead the afternoon session. So, but first I will need to change to become the CEO of Colorlist. Okay, let's start. So I need to have a magic wand. So we have 3 of them. Magic wand, and I will choose one. Lighting. Okay. Oh, here. So this is a magic wand that we designed yesterday, and we got it ready today. So the first product, okay, let me clicker you know. Okay, let's start with the back one. Okay, can you turn on the light, please? On here. Lost the clicker. Yeah, เดี๋ยวข้างหลังก่อนนะครับ Okay. Product review. The first one is the GISS lab unit on the back. We have an espresso making machine like GISS lab unit for special research and demonstration. Is the first prototype that we have made. We call GISS lab unit. So if you want to explore the superheated slurry state of metal, we can use this. So the price is 59,000 US dollar or euro. And the next one is on the back is GISS Giga unit. This is also the first prototype that we have made. It can produce up to 100 kilo of slurry, and it can be used for giga scale casting machines. So these 2 are the first prototypes in the world that we have made. And we have just made, I think, the record of making 60 kilogram of semi-solid by using this giga unit. And the price of the giga unit is 279,000 US or euro. And we will see who will be the first in the world to install this unit very soon. And we have another new technology. We call it GISS Future Cast technology. And I will make the magic wand to open it. Okay. We now can cast 75 in any shapes and form, and then anodize in any colors. And this is a demonstration of success. It's a champagne bottle made from 7075 near net shape, and it's coming soon. We don't have the price yet. And this one is the first sample made from this technology. It's not perfect, but I think it's a good start. And maybe by the right timing, I will put in champagne and we can celebrate. And it will never break. Wine bottles, champagne bottle, gas bottles, anything. It could have the strength of 500 megapascal, 5% to 10% elongation, lighter than steel. We will work on that with our partners. So this is the latest. The latest means we just got it today, this morning. Along with this, just 5 minutes ago. So thank you. So it's top secret, I will keep it. Okay, the next one is colorless products. We will save the planet by using GISS technology. So, magic wand. The first, let me show. Colorless cools. I'll be sure. We make an inhaler, anodized with magnet. If you feel fainted, you can inhale this, and it's being made for colorless products that we can anodize to different colors. And the price is 39 US dollar or euro. And we have in stock today. If you like to buy, you can contact our sales team. Okay. The next one is colorless dumbbell. Again, I need a magic wand to open it. Okay. It's in the box, and this is 3 kilograms of gold anodized color, aluminum, fully 3 kilo. So we are working on different products. And from aluminum, we can anodize, and we can make many products. So one that's being used as awards for us. Okay, so we have 3 kilo, and we're planning to make 5, 10, and more using composite technology later on. And the price, oh, hold on. So the price for this is 99 US dollar or euro, and we only make limited editions. So we only have a few more left. The first person who got this was Bell CEO, the first one to buy it, and maybe we only have one more left. Thank you. Okay. The next one is colorless bonsai. Okay, magic wand. This is also limited edition, handmade. So I adjusted myself, and our team decided. We got the special stone, and we cast the Buddha by the GFC process. And the price is $299 because we only have made 2, limited edition. Okay. And the next one is colorless waste one. So when we can cast anything and anodize, we can do many products. And this one is casted by 6000 series and anodized. So this one is near net shape casting to any feature. 6000 series, 7000 series, and anodized without any surface treatment. So you can take a look after this. And we are selling at $299 because we don't produce anymore. We only have this left. The next one is colorless mortar. Okay, let's open it. This is the mortar that we are developing. ช่วยออกมาแล้วตำให้ We can cast into any shapes and anodize into different colors. So this one premium products. And the price is $99 US. I need to present. So in Thailand, we make a lot of som tam, papaya salad. So we use a lot of these. And we are also working on other products for mortars that will be sold around the world. Colorless backpack. Backpack, please. So I will give you the endless applications of casting 7000 series. So this one is a backpack. This one is GISS technology, another one. Spider show that.
How to use.
Yes, how to use. We started the development, and then now we made by handmade later, and it can be anodized and also laser mark. Another one is a gift to my love friend, Mark. This is your birthday gift.
My birthday gift.
Yes. How old are you? Trickno.
Ah, cool.
Handmade, everything handmade.
So nice. Thank you very much.
Thank you.
Thank you.
Thank you. Thank you for coming.
Cool. When can I order?
You need to see the price first. You will not order it. Because we made it by hand for all the parts, from the leather and everything. So we made this prototype. It's just finished this morning. So we'll be very surprised for you. And the price is $299.
Is that for Trickno?
For Trickno. Special. We can discuss later. Maybe 20% discount. Okay. And before that, I will show luggage. We are also developing luggages because we think we can cast the whole luggages. So these are just prototypes. เดินได้เลย เดินบนได้เลยนะครับ It's 100% aluminum. All the parts. It's less than 4 kilo. Fully no plastic. 100%. We plan to make 100% 7075. So these are the prototypes. So we can, this aluminum, every parts. And we make it lighter than the normal one in the market right now. I don't want to tell the name. So we are working on casting the whole thing in single piece. So this is the first one, and no pricing yet. Okay, thank you. The next one is the metallic wood artwork. As you can see, we laser cut wood into shapes. And this one, I don't know, is in Chinese?
Yes.
Wrong, okay. So then we cast aluminum inside without burning. But it's not normal aluminum, it's GISS slurry. So we show that if wood doesn't burn, your die will last longer, maybe 3 times, 4 times. Some of them can make into 5 times that they don't say anything. Because wood doesn't burn, your die will not burn so easily. So that is the reason behind making this. We also cast this into table, big ones, but we cannot show it here. But we are selling this today. Oh, by the way, we got received the world-class award from New York a few years, several years ago, for material connection from New York. So it's a new material we call methyl or metallic wood. So the artwork, we also have limited edition. We don't make anymore for now. It's $39 US. Okay. เดิน present นะครับ Okay, almost the end. And this one, you know this already, is the business card made from 7000 series. In the future, we also plan to cast this business card. So it's a new way that we will save paper. And you may not need to give everyone. One of them, they can scan QR code. And 7000 series, everyone get one from your name tag as a sample. So if you like to order, you can talk to our assistant and the sales representative after this. Thank you. And the price is $39 US per set, 40 pieces, and the box. And we also have okay. magic. Oh, a prototype, colorless umbrella. No dripping water. When you are wet, you put in this. Magnet. So this is the first prototype also. We have magnet here. That's it. So this is a new prototype that we will. Okay, as the last that I like to tell is our new project, Colorless Home, that I will be focusing next year. We will make the future of longevity living, self-sustained organic retirement community that is affordable, accessible, healthy, and sustainable. Because I plan to retire soon, so I will make one for myself. So thank you for this session, and the next one will be from UFO. Thank you very much.
Okay, let's start. First, thank you everyone to come here to join our forum. And this afternoon, we will talk about for more details about your casting. I think most of the people come here want more care about your castings, your defects. You want lower cost. Now let's talk about this. My presentation is talk about how to apply GISS to HPDC and GDC successfully. And you know, last 9 years, I joined GISCO. I joined GISCO now this year, almost 10 years. And I look around over the world, and I stay in China. In China, we have sold about 80 units only in HPDC area. It's a pity that maximum 10% of customers really use GISS well. They are almost 90% feel it's real, but that's the reason I want to clarify how to use it, how to make it successful. But another thing is for Dyson. I think this morning, you know, Dyson have installed almost 20 GISS units. They use about more than 3 years. It's really used very well. We learn why we ask ourselves why they use it very well. What's the reason? Today, I think I will give you some answer. First, this is my content, and we know even joint size, the three process in castings. One is melting, filling, solidification. If you are foundry man, all focus on 3 processes. In melting area, you need a clean metal, now oxide film, degassing, hydrogen, everything, and the right chemical composition. Once you have clean metal, the next step, filling your cavity. No matter you high speed or low speed or gently filling your cavity. But during your filling your cavity, you need to control the flow behavior of your filling to avoid gas porosity and some biofilms too. So this will connection with the mold design, because the mold design will control the gating directions and flow too, and also the process optimization, like normally it's speed. And last one, after you fill in your cavity, okay, I finish 100% fill, then you're just waiting to solidification. During solidification, you will have shrinkage porosity. In this stage, you need feeding to give pressure or the temperature gradient to reduce the shrinkage porosity. So what it is, we talk a lot, but I want to use a simple explanation to explain it again. GISS is gas-induced superheated slurry. How do we make it? You have ladle, normally near liquid is higher about 20 to 30 Celsius. And then you have metal in ladle. We have a probe. This probe is porous. You can see that like porous graphite. It's a lot of holes. The probe have inside we have a cooling control. We control the temperature of a probe is about 60 Celsius. 60 Celsius probe dip into about 100 Celsius metal. The metal will be solidified on the surface of a probe because cold, it will solidify. But at the same time, we have a nation from inside to blow outside. We will blow out the surface, the solidified surface solid particles into the metal. That's only this. This is a concept of GISS. Very simple, 2 or few seconds. Then we will get the solid in liquid. Okay. Why do we call it superheat slurry? I think Tommaso also explained a lot, but I want to explain again. First, normally for liquid castings, we have some superheat. It's fully liquid. Have some superheat, and we start here, and lower solid fraction. When we below the liquidus, we will get you will in the liquid solid range. It's like semi-solid. In semi-solid, if the solid fraction is 5%, 10%, 20%, it still can flow like a liquid. We call it a low solid fraction. And once it's continue to cooling down, have lower temperature, and near the eutectic area temperature 575, you will get high solid fraction like a slug. It's like traditional semi-solid. It's very high solid fraction. It's a lower solid fraction. But all this process is beyond the liquidus, because below the liquidus, you will get the equilibrium. This is equilibrium conditions. It's fixed the solid fraction, fixed the viscosity, everything fixed. That's why this also limits the application of the semi-solid technology. But what is GISS? We are here, higher than liquidus. Maybe you cannot imagine it's higher than liquidus, should be fully liquid. Why can you get it? That's an equilibrium process. How do we make it is? It's like we always talk about. It's like a hot water with ice. The temperature is higher than liquidus. Hot water, you put ice inside, you still have solid. We call it still solid and liquid, but the temperature is higher. That's this when you cooling down, continue to wait a long time, the solid will be solid, will be remelting again because on equilibrium. But when you put this hot water with ice, put into a refrigerator and refrigerator cooling down, reduce the liquidus, you will keep that solid particles. It will be into the equilibrium conditions. Seem like this. That's the reason the GISS is superheated slurry. We are higher than liquid. Because we are higher than liquid, that's why we have no any limitation about the alloy. Any kind of alloy you can make it, no matter 6,000 alloy, even pure aluminum, eutectic alloy, aluminum silicon 12, or 6063 or 7075. That's why no limitation for air, for alloy. You can see the flow, the flow behavior is different. When you continue to cooling down, it's like a semi-solid. This is 356 alloy. It's about 50% solid fractions. Okay, that means GISS process can make any solid fraction of semi-solid slurry by cooling speed and time control. If you want high solid fraction, just wait. You're cooling down, you get high solid fraction. If you want the lower solid fraction, just short time, you can control when you put into short speed, you control the slow speed. Slower or faster, you will get different solid fractions. Okay, for any flows, the flow behavior only controlled by the Reynolds number. Or no, the Reynolds number. In Reynolds number, if higher this is a velocity, this is a viscosity. For any liquid die cast or liquid casting, we only control the velocity. Because fully liquid, you cannot change the viscosity. For gravity castings, you very gently slow casting, the feeding speed is lower, less than 1 meter per second. It's like a laminar flow. Like very gently to feeding, very slow. It's like a squeeze casting or the gravity casting or low pressure casting, all is very low velocity, gate velocity. That's why the gravity casting, low pressure and squeeze, all is like this, laminar flow. But for die cast, it's like this, turbulence flow, because the gate velocity is about 40 to 60 meters per second. It's turbulence. Why? Because velocity is high. That's why you will have porosity for sure, gas porosity. And after filling, you will control the solidification. For normal liquid solidification, it's a smooth surface. You will solidify from a cold area to hot area, and you will get a dendritic. In the last solidification area, you will have shrinkage, because from outside to inside. But for slurry, it's a little different, because at the start, we have some nuclear and solid particles inside everywhere. During solidification, this nuclear inside a hot area will grow up and spontaneously to feeding reduce the shrinkage. That's the different, the GISS. GISS change the viscosity and change the flow behavior. Solid particles change the solidification behavior. That's why I can reduce the shrinkage porosity. That's the concept. And the impact, like summary, the impact of solid particles, any particle, only 2 to 5% of solid particles is about 5 to 10 micron, very small particle size, like nuclear. We change the viscosity, we change the flow behavior, reduce the gas porosity. We still have gas for GISS slurry. Change the solidification behavior, reduce the shrinkage. And also, because our casting temperature is lower and the metal have less heat content, you will have less thermal fatigue. And then you will have higher, longer die life and reduce the solidification time. You will get faster cycle time. So, how do we combine the superheat slurry with casting process? This is the current casting process. The low LPDC, counter pressure, medium, squeeze, die cast. We can combine any casting process. Just before it's liquid, fully liquid. Now it's hot water with ice liquid, seem like liquid. That's why we can combine the HPDC, we can combine the gravity castings and combine the squeeze. Now we talk about the HPDC, and we know for conventional HPDC is normally, I think we're familiar with this, ladling power into a short sleeve, and high-speed gate velocity to fill in the cavity is about 40 to 60 meters per second. It's like turbulence flow. You definitely have gas. You cannot do heat treatment easily. You will get blister. That's why for key defects for HPDC is gas, porosity, and shrinkage porosity. How to solve this? Use vacuum. If you have vacuum, definitely you have no gas. You can reduce the gas porosity, and also you use squeeze pin to localization to pressure to feeding your hotspot area to reduce shrinkage porosity. And also jet cool. Jet cool will move the hot like this. You can see this has shrinkage porosity. With jet cool will move the shrinkage here. When you mix CNC, you cannot see the defects. But all of this will be increase the cost, the operation cost. And also, for HPDC, there are these 6 key parameters in your process. One is slow speed, high speed location, and VP change, when do you feeding, and how much the interface pressure. And from 1 to 5, all controlled by your machine stabilities. If your machine is stable, it will be stable. Normally, no change. And also another one, last one is temperature, is metal temperature and mold temperature. For slurry, same. All these parameters you need to optimize. It's same concept. And Yeah, and here the difference is the process flow control is we normally for die cast we only care about the git more optimized velocity, git velocity, but they cannot control the viscosity. For slurry, we give you another parameter, we call it a viscosity control to control the renal. If you want to get higher salt fractions, higher viscosity, the renal number will lower, and we will get less turbulence. You will get less turbulence. So this is laminal is turbulence. What we are doing for optimized GISS is between here to here. You can get anything, any fluid behavior by velocity and viscosity control. This is the difference. Normally, if you do HPDC, you only change velocity, gate velocity. And for the viscosity control, you can see, that's why we call it the viscosity control process for slurry optimization, process combination. Here you can see this is liquid, this like flow, like fully liquid. When you solidification, outside is solidified, inside is still liquid. We will get shrinkage. But for this, the flow behavior, this similar like filling your die or filling the short sleeve, the solidification will be increased because cooling down, the solid fraction will be higher viscosity. You can see the flow is totally different flow behavior. That's why you use the same gate velocity, high viscosity, less turbulence. And then when you continue cooling down, you get high solid fractions. And also, this seems like this also can explain how to reduce the shrinkage porosity, the inside and outside uniform solidified, not like liquid from outside solidified and inside still liquid. That's why we can reduce the shrinkage. So for GISS process, HPDC process, we need to control the viscosity. What kind of parameters affect the viscosity? One is metal temperature before GISS. Now we suggest liquidus plus 20 to 30 Celsius, such as ADC12 alloy. Normally we cite your holding furnace 620 plus minus 5 Celsius. If your holding furnace big variation, solid fraction will be variation, viscosity will variation, gas porosity will variation. This is the key. The first step is you need to control your holding furnace stable plus minus 5. At least if plus minus 2, definition much better. Secondly, once the start temperature is stable, the GISS time we call it you will get initial nuclear quantities. That what I mean, if you dip 1 second and 10 seconds, the number of the solid particles is different. Only the number. Not people want. I saw some companies, they have GISS, they bubbling 20 seconds, 30 seconds. They want to get globule grain, a lot of solid particles. No, you will remelt, because higher than liquid. Sometimes if lump bubbling, if higher than liquid, you will remelting the solid particles. That's why we develop the maximum. And also we suggest the maximum dip time. A dip time is less than 10 seconds. It's good enough. And the last one, and another one is the short sleeve temperature. Short sleeve temperature, you can, because if short sleeve temperature is very cold, when you pour in slurry, two things. One is you will get cold flakes, the bottom cold flakes, like oxide fumes, cold flakes in your in your part. And secondly, the short sleeve temperature also really affect the solid fractions. If your short sleeve temperature is cold, ignore the cold flakes. When you pour in a superheat slurry, the metal quickly below to the liquidus. The nuclear solid particle will grow up. The viscosity will quickly increase. That's why it's very important. Normally, we suggest a short sleeve temperature slightly higher to avoid cold flakes, and also we control another thing. We control the slow speed. Slow speed. If slow speed is very slow, the solid fraction will be increase. The viscosity will increase because cooling down. That's why normally we will compensate the heat loss. We use a faster slow speed and also to avoid entrapped air in short sleeve too. And the last one is another one is high speed location. Normally we start the high speed to prefill the cavity maybe 5%, 10% or 20%, push air out and increase. And last one is mood temperature too. Mood temperature also if too cold during your feeding process. You can imagine when you have slurry, you pour into a short sieve, and that time the solid fraction is continuously increased because temperature reduced gradually. That's why the mood temperature also change the flow behavior too. And here we do some simulation to show. This I use a castle. This simulation use a C3P, and now use a constant viscosity. So far, haven't any commercial software can simulate a GISS process. Then we collaboration with Castle software to get the commercial GISS model to do simulation. Later, Tommaso will do the more details, talk about that too. And here I just use a constant viscosity because the feeding time is very short, normally 20 to 40 milliseconds. I use a constant, no any change during your feeding of viscosity. I just to show the difference. This milk is about 3. The unit is for the viscosity. 3, 10 times, 100 times, 1,000 times. It's honey. It's like our honey. It's very high viscosity. They use the same speed. You can see the flow behavior totally different. This is turbulence. This is laminar, like this. Yes, that's why for GISS, you can do 30, 300, or 300, 3,000, any sort of fraction you want. But this is based on your product. Our target is find the right viscosity to get the good part for your part. That's not easy too. Because if this only the Renault different, viscosity different, and also we try the kit. If the kit velocity is 33 millimeter kit velocity, it seems like normal die cast. Again, you can see the higher viscosity, less turbulence. But you can see still in trapped air, you need the gating here, venting here. It's different. And higher viscosity, even and higher gate velocity, we have less entrapped air. That's why we have lower porosity level. Here I give you a real example. Here is about, we do this very interesting test. This is fully liquid. A 380 is about the aluminum silicon 9 copper 3 alloy. We ladling and cooling in the air. You can see to tilt it at 570 about liquid eutectic temperature and power on, it's like a solid. Because dendritic, cooling in a big dendritic and combined together, not easy to cut. And you can imagine this same alloy, mixed slurry, same temperature, totally different. That's why, because this dendritic, they combine together. This is non-dendritic. Still liquid and non-dendritic seem like a flow, still can flow. Same temperature, still can flow. This is also can explain why slurry can make the part at a lower temperature, lower 40 Celsius, 620 or 610, compared to liquid. For liquid, 570 cannot flow, but for slurry, 570 still can flow. That means you still can use lower constant temperature to make the good part, no misrun or non-feeding issues. And also you can explain we also can explain the solidification behavior also different. It's uniform from outside and inside. Yes, and after feeding, again, feeding your cavity controlled by the viscosity and velocity. The last one, after feeding, you need the feeding to reduce shrinkage, porosity. What parameter affect the feeding? One is mood temperature. Hotter dye, better pressure transfer, can reduce the shrinkage porosity, and the pressure build up. After feeding, because slurry, the casting temperature is lower, you need to feed in earlier or faster after feeding bond feeding. Not too much delay. And the third is the total feeding time. Because after we optimize the slow speed, high speed, the longer feeding time, the higher solid fraction. Because cooling down, with higher solid fraction, you need to better feeding too. And the GISS time only affects inertial nuclear quantities, how many solid particles you will get. And the thicker gate, for the mode, normally we like thicker gate because thicker gate is better feeding to pressure transfer. And this is a general concept on the slurry mode design. It's general, not some accurate, because it's based on our experience. The gating system design follows the liquid. It's still like liquid to filling, the filling behavior. No, the direction. That's why the similar like liquid die design, but we like the gating thickness slightly thicker than liquid gate. Just want to compensate the pressure feeding. And also, the venting thickness is thicker. Why? Because we use slurry, we can normally for the high pressure, the chill vent, the thickness is about 0.4 millimeter. Normally we can increase about 0.8 or 1. The bigger venting push air out, but you have to put your venting at the right location. And for more details about the mode design, we will later the GX will talk more about the mode design. This is a case study. This is from the failure or this is from the air compressor. You can see we do this CT scan, the liquid temperature, and also want to, we also low temperature 625. Liquid also can make this part. And liquid 25 GISS 3 seconds, make slurry. No any change, no any process change. Just use and without GISS. This is 5 seconds. You can see this is a very good example. The increase in the GISS time, more nuclear, slightly higher solid fraction, higher viscosity, reduce the renal, less turbulence. You can see the porosity level, 0.2 and 0.17 and 0.13 is reduced because of GISS time, because high viscosities. But the maximum porosity is bigger. You can see this area is shrinking, hotspot area. Why? Because that's maximum porosity, most are shrinkage porosity. Because our feeding is not enough. We haven't optimized anything, just use and without GISS to compare. And after optimization, we have, this is the original GISS conventional liquid, the slow speed, high speed. But here you can see we increase the slow speed to compensate less heat loss in short sleeve, and also compensate the feeding because we want to reduce the shrinkage porosity. And also we prefill. You can see here we started the high speed about 420. Here is about we started 300. Here is start here about 350, something like that. We prefill to push air out. You can see the porosity level reduce a lot, 0.2 to 0.6, something like that. To better feeding and push air out. That's the key. We need to find this, find the new curve for feeding, new curve, optimal curve for plunger velocity, and also compensate feeding. And so we compare the parameters. You can see the metal temperature will reduce, and the mood temperature we want higher. We compensate higher by reduce spray, fast cycle time, get hot die. No need to. I want a heater. No need. You just hot die, reduce the spray, reduce the solidification time, fast cycle, and slightly optimize the slow speed higher, high speed same, or reduce. It's based on your part, and the prefill and the pressure build time, pressure delay time less, and the intensive pressure. If you have a hot die, you can reduce the intensive pressure. This gives you a chance to use a small machine to make big part, and also sleeve temperature and GISS time. In the end, in summary, GISS process is a viscosity control process. It's not the same as before. We only control the velocity. This process is feeding compensative process. How to compensation, hot dye, a for mode, thick gate, to better feeding, to reduce pressure too. Also, if you don't want to change anything, it's okay, it's still okay, but the benefit will be less. This is our standard trial plan for the HPDC process. Normally, we have a 4 step. Step 1, normally we will try the GISS time, 3, 5, 7, or even 10. Why? We want to know this liquid baseline first, and then we want to know what is the best GISS time, what is the best sort of fractions for your part. For your any part, you don't know how much solar fraction you want. That's why we try 5, 3, 5, 7. If 7 is good, that means this part needs a high solar fraction. If 3 is good, that means this part 3 is enough. And then we fix the GISS time, find the best slow speed, the V1. V1, normally we increase about 10% to find the best slow speed. And then we find the best high speed. And then we find the best switch point. Switch point, all for these procedures. If it's good, and next, if it get another level, if you want to move forward again and repeat to optimize. So we use HPDC concept to design the mode with thicker gate and thicker vents. This is very simple. Other is not follow the liquid. And we use a constant viscosity to see the slurry help. And we collaboration now with PQ2 Castle for the GISS simulation with commercial GISS model. With Thomas will talk more later. We use compensation model in GISS trial. Compensating slow speed, high speed equation, and hot dye, hot sleeve to compensate. And now GISCO can provide GISS turnkey mode service with our mode partner GX together. For gravity, we do this test, and we know for gravity casting, normally we use 356 alloy. The casting temperature is normally higher, and then you need a big riser for feeding. But for slurry, our casting temperature start about 630, and the die time, we can reduce a lot die time, and also shrinkage to increase the material yield. This is a target for the gravity casting: reduce riser, increase material yield, reduce die time for fast cycle. And here we also do we compare. You can see the temperature reduce the shrinkage and riser, increase the casting yield, and better strength and elongation to fast cycle, and energy saving a lot. And we do this test also to measure the temperature of solidification time, reduce a lot. This is we don't use a grain refiner, just no tie bond, just to compare. No grain refiner and use GISS and similar. And this is we collaboration with Bio and to provide the turnkey gravity mode too. We develop this part to test. For this part, for more details, BIOS, we will talk about later. You can see the sand core and insert, steel insert, everything, very thin part. Before, is a liquid from bottom, counter pressure. This counter pressure, this use a tilt. And the casting temperature and the short weight, you can see material yield from 30 to 76. And cycle time reduce a lot. That's all. Any questions?
Any questions? I think very clear. You touched everything.
Thank you.
Thank you. Okay, another gift for you. Okay, we will follow schedule before coffee break. One more. Yufeng, could you introduce our next speaker?
No, you use this one. Use this one. Yeah, hold on.
So we will have one more speaker and we'll go for a break and we'll come back for 3 more.
Yes. Next
no,
one.
2 more. Yeah.
Next one is a GISS slurry HPC mode. Let's welcome Mr. Xu Jian to give us the presentation.
So Yufeng will make the translation.
Make translation. Sorry. Hello. Yeah.
各位下午好啊！
Good afternoon, everyone.
我来介绍一下半固态压铸模具设计。
Let me introduce the GISS slurry HPC mode design.
我的公司在那个中国江苏啊，在那个南通，占地面积大概有2000平方米，啊，离上海的时间大概是有2小时，啊，我们是从2002年开始就跟 GISS 合作了，已经成功交付了将近50套模具。
Hold on.
啊。
Yeah, our company is about 2,000 square meter. It's about 1 hour, 1 to 2 hours to Shanghai airport. And now we collaboration start in 2022. So far, we have delivered more than 50 turnkey modes together to our customer.
好，这是公司的一些产品。
This is some typical EV auto parts they have delivered.
介绍一下是吧？这个主要是一些新能源的裂变器的壳体啊，水道部分的。
Yeah, most are from EV part for the inverter, EV inverter.
这个就是一些有一些安防的，这个底下那个是那个电动汽车的那个插头，这个是端板啊，那个是卷线器，最这边的是卷线器。
And the top is a heatsink and also plug and some for EV battery plates for laser welding.
那半固态模具的一个从开发到交期，那从250灯到3000灯以下的模具，平均天数大约45天，啊，那开始就是采购订单，慢一点啊。
Normally the total lead time from 250 to 3,000 tons is about 45 days from start get PO to deliver, including the trial run.
那就下一个。那我这边重点的就介绍一下那个半固态模具设计的一个流程。
Now I will introduce the process flow and for the slurry mode design.
首先获取图纸的信息。
Yeah, first we will get the casting requirement.
然后确定一个充填时间。
And then the first step you need to define the filling time.
那再来我们要确定胶口的大小。
And then determine the gate area.
然后再往下是找到合适的分形面合适的便于加工去除的一个位置来进料。
And then find the right gate location and the layout is it's easier to cut trimming.
再来就设计排气，也是在那个胶口最容易去除末端的地方来设计排气，炸包排气。
And the last one is overflow and vents to design.
来用 PQ 找到一个合理的机台。
And then based on the PQ analysis, find the right machine size.
找一个合适大小的冲头。
And the plunger.
纳入那个模流分析。
And when we finish this, we will do the simulation and analysis.
哎，我重点介绍一下，现在是用我下面模拟的是那个用的 magma 还是液体的，后面会用那个 Castle 软件去做半固态的一个模拟。
And in the later, we still use a magma to make some simulation. Still follow the liquid because no commercial model. And later we will use a castle in future, collaboration with a castle software.
哎，
下一页。
下一个是一个，啊，我来举一个例子。
This is a case study.
这是一个铸件，它的一个表面积，然后材料是 ADC 12，那大小呢是这个面积的大小是251乘204乘123，然后重量是由1575克，平均壁厚呢有4.75，最厚的地方就是热节点的地方有13.72，最薄的地方也有1.29米米。
Yeah, this is a very typical part. The part name is a housing. The alloy is about ADC 12, and the dimension is there, and the part weight is about 1.5 kilogram. And the key is the average thickness is very thick, about 4.75, and the minimum thickness and the maximum thickness is big range. This is very challenge for the liquid die cast.
这个产品呢，我们先用半固态的这条公式来大体的推算一下。我继续，它的面积呢有583我们设定30米每秒
OK.
好，你要么你先。
And first, this equal. We define the filling time based on this is from NACA, PQ, and GT manual to confirm the filling time, and then based on the cavity volume and the gate velocity, we set gate velocity 30 meters per second.
料温我们半固态的是用620。
And we set the gate temperature about 620 Celsius.
到模具琴铅的表面的温度是350。
The surface temperature of the mold is about 350 Celsius.
凝固的时候，就是在模具里面光凝固接近凝固的时候是593。
And the solidification analysis start temperature about 593 Celsius.
对，那个壁厚呢大概是4.75米米，就是这个基本上用这个公式大体的去推算一下。
And the average, we use the average thickness about 4.75 millimeter, and then we follow this equation to get the filling time.
那如果 P 扣再算一下，那我们用压铸机的最大的50%，最小的30%，用中间这一段。
And we use a minimum gate velocity, gate speed from 30 to maximum 50 meter per second, and follow the process window. The point is in the right process window.
这个是模流上分析的一个热节点。
This is a hotspot analysis. You can see many hotspots. You have the risk of the shrinkage porosity.
肉料、流道、炸包。
And this is a gating design system. And you can see the gating direction is follow the gating directory to follow the hotspot analysis to reduce the porosity and for better feeding. And is a gating and runner and overflow.
滑块、动模、地模、分形线、滑块。
And then we design the moving side, fixed side, and parting line.
刚刚已经介绍过了这个，没用哦。
This is you will use a magma to, and we say this is the feeding behavior. The feeding direction is similar like liquid during feeding, but the viscosity definition is different. That's why later will apply the Castle software for GISS simulation later. Use a commercial GISS model.
好，下一个。
再按一下。
温度场的模拟。
Yeah, this is for the thermal simulation. The temperature distribution.
没错。这个是根据热节点啊，然后设计的那个水路啊，模温系统。
Yeah, based on the hotspot area and the final design the thermal balance, the cooling channel, to get uniform mood temperature.
这是公司的一个模具制造的一个流程，以及制造的一个流程，材料入库、深孔加工、初加工、热处理、组装、量测设备、抛光，然后精加工的一个流程。
Yeah, this is our mood manufacture process flow from the material, purchasing material and deep hole machining, rough machining, heat treatment, finish machining, polishing, and the mood measurement, and then assembly together, then make trial.
现有设备。
This is our current manufacture capacity.
这是设备的台数。
This is from CNC, EDM, CNC. This is the capacity of their current company.
试模的一个过程，这里重点说明一下，我们试模是用精确计算的。
And also our mood trial plan. This is our mood trial plan, and everything will be make calculation before make trial to get every data.
算好之后，直接输入压铸机台。
And then put into the parameter into the machine, and then make trial.
我们重点监控模温跟喷涂，然后开始试模。
And we pay more attention on the mood temperature and the dye too.
这个试模后的一个，以这个例子来讲，就试模后的我们 X-ray 拍的一个效果。
Yeah, this X-ray of this part, you can say very less porosities.
这个是简单的一个包装出货交付。
And after the customer, we deliver the sample to the customer to confirm, get that confirmation, and then package and deliver it to customer.
谢谢大家。
That's all. Thank you. Any question? The 时间是吧？
时间吗？
胶壳大小。
啊，就搁前面。
模具胶壳设计那个。
哦。
胶口大小，你有那个壁厚嘛？喂，根据它的壁厚，那预估一个充填时间，有了充填时间，你就好算胶口大小了。那你多少毫秒？你要多少毫秒把这个最关键的，你多少毫秒把这个铸件能够充填完成？
我再解释一下。它是你问那个胶口的那个大小嘛？对，体积是知道的，对吧？铸件体积是知道的，然后那个充填时间是知道的。胶口的体积除以时间就是流量。
可以得到它的胶口的面积。
胶口的流量。流量等于胶口的速度乘以胶口的面积。
所需要的
速度你要给它一个，面积就出来了。
对。
Okay, let me translate. Sorry.
你推算一下就可以了。
Let me translate. First, his question is how to confirm the gate area, the in-gate area, and first we know the volume of the castings is fixed. We know the volume. we know the filling time, how many times you fill these cavities, maybe the 20 or 40 milliseconds. We have volume, we have time, and volume divide time, we will get the flow rate of gate flow rate. The gate flow rate equal to the gate area multiply gate speed. Gate speed. Then you have to confirm, give fix the number of gate speed. How about the 30 meter per second? You have gate velocity, then you will get gate area. How much area you want? The gate area equal to the gate thickness multiply the total gate length. At this time, you need to confirm the gate thickness, how much you want. If 3 millimeter, then you will get gate length, total length. When you have length, you need to confirm you want to use one gate or multi-gate to fill your cavity. That's all. Any other questions? If no, we have coffee break.
Yeah.
Oh, keep.